Hey guys, welcome back. Today we are going to be talking about neutralization reactions, and there's a little bit more in the CK12 passage that I had you guys read than what we're going to go over today, just because some of the stuff like net ionic equations I'm not super concerned with. Um, but I really want to focus just on neutralization reactions. This is what happens anytime an acid and a base get together, and it's the same thing that happens when you take an antacid because your stomach is too acidic. Um, and it's the same thing that happens when vinegar reacts with baking soda and it fizzes. That's a neutralization reaction. But they're actually pretty simple. And if you go back to the beginning of the semester when we talked about reaction types and recognizing reaction types, a neutralization reaction is just a more specific classification of a double replacement reaction. So if you remember, double replacement reactions require us to have um, a positive and a negative ion in one compound, a positive and a negative ion in another compound, and essentially the positives just trade places. So in this case, the H is going to trade places with the Na, leaving the negatives with new or dance partners. So that was a couple months ago, but hopefully you remember a little bit of that. So if you look at what's happening here, the H here is now going to be paired up with the OH, which if we look over to the other side of the equation, we have H2O, which would be the same thing as HOH, right? So we don't typically write it HOH, we write it as H2O, but it's the same thing, okay? It also means that the sodium, the Na, is going to be paired up with the Cl, the chloride. And that's exactly what we have over here, NaCl. Notice I've put them together in a 1-to-1 ratio, and that's because the sodium is +1 and the chloride is -1. Now normally we would get out a periodic table to discuss positive and negative charges, whether it's +1, +2, -1, -2, but we don't really even need to do that here because the formulas on the left side of the equation tell us the charges. The reason I didn't put a subscript here on Na or on Cl is because when I looked at the left-hand side, I knew, even without looking at a periodic table, that Na was +1. And I knew that because it is in a 1-to-1 ratio with hydroxide, which is -1. The same thing with I'm sorry, the same thing with Cl. It's -1 because there's only one H with it. If there were two H's, then that would be a hint that Cl must be -2. If there were three H's, that would be a hint that Cl would be -3, right? But there's not. There's one of each, so that means the Cl must be 1-. So if I have +1 and -1, which again I figured out just by looking at the other side of the equation, then it's just going to be a 1-to-1 ratio, all right? So let's try this where it's maybe not quite a 1-to-1 ratio. Let's try HF plus BA. Oops, handwriting gets terrible sometimes. BaOH2, all right? And let's think about what that's going to make. Now the first product is easy. The first product is always going to be when H pairs with OH, that's always going to give you what compound? Right? It's going to give you water, H2O. Now we could do the charges for the H and the OH to come up with this too. We could look at that because H is +1 and OH is -1. It's a polyatomic ion. Its charge never changes. And so when I put them together, if I have +1 and -1, I don't need multiple of either one of them. I need one of each. And then the last step is just to rewrite it instead of HOH, rewrite it as H2O. All right, so let's get back to the potentially tricky part, and that is what is the other compound, the salt. Okay, so when we say up here we're producing water and a salt, notice I put salt in parentheses. That's because it's not always table salt. NaCl that we form. When we hear the word salt, that's what we think of, the stuff that you put on your French fries or your popcorn. Okay, and that's actually what NaCl is. Um, but it's not always NaCl. A salt can be any ionic compound, essentially, at least for our purposes here. So what will that salt be in the case of this reaction? So we're going to have, okay, so what is the other positive ion on the left side of the equation other than hydrogen? There should be another positive, right? So you should have said that barium is the positive ion. What's the charge on barium? You don't have to look at a periodic table, remember, you can just look at the formula. Okay, so you should have said that barium is positive 2, and the reason we know that is because there were 2 hydroxides, and each hydroxide is minus 1. So that one single barium would have to be positive 2 in order for us to have balanced charges. So then what's the negative ion on the left side of the equation other than the hydroxide? Okay, so you should have said it's the F, the fluoride. And then what's the charge on the fluoride? Okay, so once again, all we have to do is look at the ratio. If it's 1 to 1 with hydrogen, and hydrogen is plus 1, fluoride has to be minus 1. So when I put them together, barium with fluoride, what is the formula going to be? Okay, so you should have said, when we put them together, Ba is plus 2, F is minus 1. So when I put them together, to balance charges, I would have to have 2 fluorides. All right, and then the very last step would be, how do we balance this equation? Okay, and you should have said, I need 2 fluorides on the left to match this 2 on the right. So the only way to do that is by putting a 2 out in front of HF. That gives me 2 hydrogens here plus 2 more here. And so that would be 4. And so I have to put a 2 in front of water. Okay, that gives me 2 oxygens, because remember, this subscript doesn't go for oxygen, it just goes for hydrogen. So I have 1 oxygen here times 2 is 2. And then on this side, I have 2 distributed into the hydroxide in the parentheses of 2 oxygens there as well. So this thing is balanced. So the last step is I'm just going to get rid of all these charges and all this extra stuff. And there is my balanced equation. Okay, let's try one more for practice before we go here. All right, let's say I have AlOH3, aluminum hydroxide, and that is going to react with H2S, hydrosulfuric acid. So see if you can tell me what the first product is going to be for this reaction. What's going to happen to the hydrogen and the hydroxide? Okay, so that's going to give me water, right? I think at this point, hopefully we've established that that's a pattern, right? We get water every time. And I don't really have to list it first, but just to keep things simple, that we've done that consistently. Okay, so what is the positive ion that's going to go into the salt? All right, you should have said that other than hydrogen, on the left side of the equation, the other positive ion would be aluminum. So now we're going to have aluminum, and aluminum is going to be paired with what negative ion? What's the other negative ion besides hydroxide on the left-hand side of the equation? Okay, yeah, it's sulfide. Now we could look at a periodic table and we could figure out the charges for sulfide and aluminum. Aluminum is in group 13, so it should be plus 3. Or I could look over here and see that there are 3 hydroxides, and that tells me that aluminum must be plus 3. Either way, I've got a plus 3 charge in aluminum. Same thing with sulfide. It's in group 16, and everything in group 16 is minus 2. So I know it's minus 2. But I also could just look at how many hydrogens there are over here. There's 2 hydrogens. That must be balancing a minus 2 charge on the sulfide. So if I have positive 3 and negative 2, I have to use the least common multiple to come up with the formula. So what is the least common multiple of 3 and 2? Okay, so you should have said 6. So how do I get to positive 6 if each aluminum is positive 3? I need to have how many aluminums? Okay, I need to have 2. How do I get to negative 6 if each sulfide is negative 2? All right, I need to have 3 of them, right? And there's my formula. Now all that's left is to balance. And when I balance this one, it looks like maybe the easiest thing to balance first might be the aluminum or the sulfur. I don't know that it matters. We'll see. Aluminum, I have 2 here and only 1 here. So let's go ahead and put 2 out in front of aluminum. Sulfur, or sulfide, I should say, we have 3 on the right, only 1 on the left. So I'm going to go ahead and put a 3 there. Now that's going to give me an awful lot of hydrogen. So if I look at the left-hand side, how many hydrogens do I have right here? So that's 6, right? And then over here in the aluminum hydroxide, I have another 6 because I have 3 distributed into the parentheses times 2 coefficient. So that's another 6. So I have 6 here and 6 here, that's 12. So on the right side, to get 12 hydrogens to match the left side, I'm going to need to put a 6 out in front, right? And then everything should be balanced. And those, guys, are neutralization reactions. Make sure that you email me with questions if you didn't understand what we just talked about, or come into our Zoom session. You know, we have them. What are we? Tuesday, Thursday. So tomorrow afternoon. Today's Wednesday. Tomorrow afternoon at 3. Or Tuesday at 11 a.m. So please join us or email me questions, guys. Otherwise, have a good rest of the week.